So, what we saw this far was that we basically did some data aggregation. So, what we wanted to do was to take hourly or 20 minutes interval data and aggregate into hourly level data so that we can compare different variables. And now we have this aggregate data frame with updated information about average speeds and average temperature and average Celsius and so on. So let's continue working with that. So this is indeed what we have. So it seems that the temperature has been 14, 15 up to 20 degrees, quite warmish but not that warm, which was the case this August, so it wasn't the warmest weather in Finland. What we want to do next is to see that the aim of this lesson was to find out outliers. So where there's some, do we have some information in our data that could imply of having a storm? And how we can find out these kind of outliers? Well, there are different ways of doing it, but how we define an outlier in our data. First of all, the variable that we are looking at here, so what data do we try to use to find the outlier is the speed, so the wind speed. Of course, when it's stormy, the wind speed tends to go quite high, and that's the data that we were going to use. So how we define the outlier is that an outlier is so that such that when the wind speed is 2 times the standard deviation of all the wind speeds, so then we define that as an outlier. This is one way of defining it. It's not a kind of any rule kind of. It's not something that would be kind of absolute truth, but this is what we use. And let's continue on that. So let's put my slides here. So as said, so we want to, first of all, if we define that we have the standard deviation as one kind of criteria for that, so what we need to do is that we need to calculate the standard deviation from our aggregated data. And for that, we have already seen in the first Pandas lesson how to do that kind of thing. So calculate the STD, and as well we want to calculate the average wind speed. So average of wind speed. And how we do that is that we say that standard deviation of wind equals to aggregated data. So we use the hourly level data now. So aggr data, and what is the column that we want to take the standard deviation from? Well, it's the speed, and there was that function called std, and in the parentheses without any parameters. So this is how we can get out the standard deviation of the wind. So how much has the wind approximately varied? So it seems that there's been 1.6 meters per second on average, the variance. Then let's take the average wind. In a similar manner, we say that, I'll just copy and paste these two like here, and instead of using the STD, we take the mean to get the average wind. And let's see, what was the average wind that we had in our data? Well, it was on average 5 meters per second, so not that strong. Okay, then we need to do the kind of formula to define the outlier, so wind speed is 2 times the standard deviation higher. So how we need to do that is that we create a separate variable for the threshold. So the threshold for the outlier. So for this purpose, I will create a variable called upper threshold, so that we can see that it is the up. And then we take advantage of these variables that we used. So the threshold is the average wind. So the AVG wind plus the standard deviation wind times 2. So this is the criteria for kind of specifying an outlier in our data. And let's see if I execute that and see what we have. So it seems that the upper threshold, there is something wrong in here. There is, now it should work. Yeah, still not used to these fancy American computers, although I think quite many of them are American, but still, yeah. Anyway, so the upper threshold is 6.5 meters per second, and this seems to be quite right. Or does it? No. Standard. Seems that we have a different result.
You assign something. I think you assign something.
Yeah,
to,
might. Yeah,
average
might.
wind.
Yeah, might be. Let's do so that I once more execute these, and let's see now. Okay, now it seems to be. Yeah, there was something wrong. So this is the upper threshold. So 8.43 meters per second. And of course, now we want to see if the values, so wind speeds, are outside this threshold in our data frame. So let's create a new variable, create a variable for the outliers, for outlier. So I put in the aggregator, and I create this kind of variable called outlier. And at this point I don't put anything there. I just do it like this, and then we can see that we have an empty column here, outlier, and let's then specify if we have those outliers, and we can do that by iterating over the lines and doing the simple conditional statement. Yeah.
Sorry, but what did you change from the upper threshold that you get the 8 point something?
I just I just executed these another time. I don't know what actually happened there.
Yeah, I think I do. It looked like when there was the typo that Henrik had the first time, you had an equal sign and then a second equal sign instead of a plus, and so it reassigned the value for 2 times the standard deviation to the average wind speed.
Yeah, so what we want to do is to just again iterate over those lines. So for IDX row in, now we want to iterate over the aggregated data and iter rows. And then what we want to do, we want to create a criteria. So if the row, so if the wind speed is higher than the upper threshold that we just created, then let's add a value true into the new column that we have. So the outlier column. So aggregator.log So again, if we want to update something, so we specify the index that we are at and then the column that we want to update, so the outlier, and it equals to true. If it's not, then we do the same thing, but with the false. Else aggregate equals to false. So in this way we just iterate over the lines and specify either true or false if we have an outlier in our data. And let's execute this and let's see, what do we have? Aggregate. So we have plenty of false, 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 but then we have one true. So there indeed seems to be one kind of outlier in our data. We can also check. Let's create a new storm data frame. So let's create a separate data frame for the ones with the outlier. So we just create a storm equals to aggregate.x. So this is how we can do some selections from the data. So aggregate.x in square brackets, aggregate outlier, and what do we want to select is those where the outlier equals to true. And let's try this. Well, there was this deprecation warning, it doesn't matter. But now we have a separate data frame storm where we have that one value. And as we can see, the wind speed, average wind speed during that outlier was 8.9 meters per second. It's, well, not that much. And the gust, so when there were the wind blowing hardly, it was 13 meters per second. Not really that big of a kind of storm. But of course, when we check the data, we are actually working with only 1 day, with data with 1 day only. So for sure we don't actually have enough data to actually determine really good outliers in here. So the last thing that I want to do is that now I have created this script where we have all the steps available to actually do the kind of outlier analysis. But instead of using data from 1 day only, so the sample in the website, let's repeat this with the bigger data. So now we have a bigger kind of sample of data with the whole August of 2017. So let's download that and see if we have some differences in our data. So again, so now it should be here. So I will just copy that into the same place where the original data was, and we can see that what has happened here. So there is the difference in the name of the file, so it's otherwise the same, but the sample is now equals to August. So I just copy and paste this under here and change this sample into August, and now I also just comment out this one. So instead of basically reading the data from the sample, now we take more data and run the same analysis. And this is, of course, when doing programming, this is one of the biggest benefits that you can do, that if you have a script that works with some sample of data, then you can just use the same one, take other piece of data with similar structure and just run it, and basically it should go well. So now what I do is that I just press the run button here, or F5, and do the same thing, and now it takes a while, but basically we are doing exactly the same procedures that we did so far. And what we end up having here is that in the end we should have the storm data frame, and now we are excited. Do we have some more outliers? Well, we do. We indeed do. So we have plenty of outliers, which is great. One last thing, let's try to see. So we have the wind speeds here, and then we have the gust. Of course, the wind speeds, because they are averages based on long periods of time, whereas gust is just short period of wind blows recorded. So let's see if we have some outliers in the gust. And let's do it so, well, not outliers, but let's rank and sort the data based on that. So that's the last thing that we do. There is some more stuff in the materials, but you can read it later yourself. Let's do sorted gust and how we do and sort our data. So storm, sort values by. So this is how we can sort the data and what we want to use for sorting it. So it was not the speed. Now we want to sort it by gust, and we specify that we want it to in ascending order. So we said no, in descending order. So we specify that ascending is false, which means that basically descending is true at that point. And then let's execute. Now we have a sorted list of those gust values, and let's see, what do we have here? Well, yeah, there seems to be one really big outlier here, and if you remember still what happened during the August of 12, around 6 o'clock it seems, so these are at GMT, but basically what happened at that time was that we faced this nice little storm in Helsinki called Kiira. So it's actually this that we can see in our data and find out. So this was kind of the thing that we wanted to show you during the lesson here, to kind of use real data to find out some real phenomena happening around us. So basically what we did was to try to find these storms, and indeed there were quite stormy weather in August. So let's see how many hours of storm did we have. Just take the length of the storm. So it seems that 22 hours of August were kind of outliers, so quite a lot of storm. Yeah, but that was the part for the Pandas analysis. So now you know quite a lot of new ways of interacting with your data using Pandas functions, and there are still more, but unfortunately we don't have enough time to teach you them all, and it's not even necessary. There's plenty of stuff available on the internet, how to learn how to do things and so on, so please use those. Next day we'll shortly kind of introduce you to debugging and the error handling and try to understand those.
Yeah, any questions about the Pandas stuff before we transition? Yeah.
My point is, I don't know why that worked when you do the last poll with the speed and the outlier. I have put the same as you did.
This one. Well, yeah, I can cover it.
Yeah. Okay, otherwise, yeah, we've got roughly 30 minutes, and there's definitely more material than we can cover in 30 minutes, included in the lessons on dealing with errors and debugging
So we're just going to hit a few kind of highlights from those lessons. And the lesson, for instance, on debugging, there's not really a planned activity, so that's something you can also maybe just read through a little bit. It's just tips about how to sort of solve problems in your programs a bit more quickly. So if we start just in terms of dealing with errors, you guys have seen a handful of the different error types by this point, and I'm just going to, for the purpose of the lesson here, just go into the IPython console and show some examples. So on the web version of the lesson, you'll see a list of, I guess it's 5 of the most common error types that you'll see, and as well as sort of examples of how to get those different errors to occur. So there are things like index errors that you'll see when you're dealing with lists. So if we created some list, in the example on the web page I used dogs, so we can make a dogs list. We could have maybe Snoopy, and what are some other good dogs we could include on this list? I don't know. How about Fido? That's sort of and Rover, and maybe we'll put Lassie in there, and maybe one more dog. How about
we had a lovely office dog called Panda.
Panda, all right. So we've got these dogs, and if you put them in a list like this, you could put the dogs in just as numbers or whatever you want. If you try to access one of the dogs, maybe to find out what its name is, and you put in something like dogs 10, you're going to get an error message because you're requesting a value that's outside the list length for dogs. There's only 5, and you're asking for the value in position 11, in this case, by using the index value number 10. And of course, in that case, the index value is the problem, and you get an index error. There are lots of other of these kind of common errors that you can encounter as well. If you do something like, say, my var equals your var, and hit enter, you're going to get a name error, unless you've already defined the variable called your var, because you're trying to assign something, but this value that you're trying to assign does not yet exist. You get a name error. It basically just says that variable has not been defined. Probably the most common is syntax errors, which you can get if you're typing quickly and do something like dogs, question mark equals 10. There is no operator that's a question mark and equal sign, and so what happens when you execute that, of course, is you get a syntax error saying that Python doesn't know how to do that. You've given it something it can't handle. So in the lesson, I go through an example of calculating wind speeds and converting wind speeds from kilometers per hour to meters per second in the context of visiting some place where wind speeds measured in kilometers per hour, and perhaps being more familiar with wind speeds in meters per second. And the essence here is it doesn't matter whether we deal with wind speeds or not. We could just have some kind of statement that says print my favorite dog is dogs, whatever number 2 is. And I'll type in something like this. And probably you can already see that this is going to be a problem. But when I hit enter here, I've given a print statement, a string of characters, in this case dogs 2, which is also a string value, that's no problem, but I've not included the second quotation mark here at the end of the line, and so I get a syntax error because I need to have another quotation mark here in order to have proper syntax. And in this case, it comes back saying EOL while scanning literal string, or string literal, something that means a great deal to just about everyone. But as it turns out, these messages are here for a purpose, and that purpose is to help you find the solutions to your problems. They might be sometimes a bit cryptic, but they are designed to give you the information to solve a problem quickly. And so in this case, it's worthwhile. We're just typing things in. So the file that's given here, you can see something that says file. If you get an error in a script, which is what the example is on the web page for the lesson, it will give you the name of that script file where the error occurred. I mention this because I've had the experience, probably Henrik's had the same thing, of thinking I'm working on one script in one directory and then realizing I'm actually modifying a different script in a different directory, and when I run it, I keep getting the same thing I think I've fixed because I'm actually not changing the same file that I think I'm working on. When you end up with scripts that are similar, this kind of problem comes up. So here in the error message, when you see the file, it's useful simply to look and make sure to yourself, confirm you're actually working on the file you expect. You'll also see that it gives you the line number here, and it tells you where the error occurred. This is just one print statement here, so of course it occurs on line 1 because I've typed in one line. If I had a for loop, for dog in range len dogs, and you don't have to type this in if you don't want to, because I'm going to type it a bit quickly. I could have the same kind of statement. In fact, let's go ahead and make it len dogs +1 just for fun. Print, and we'll say I like, and then dog and dog. Something like that. So I won't put a syntax error in this time, but here, when I type this in, I get I like Snoopy, I like Fido, I like Roper, I like Lassie, I like Panda, and then trouble. That is an index error because, of course, I'm now trying to access a value that's outside of the range, because I said use the range of dogs and then +1. Okay, there is no dogs +1 value to find, and I get an index error here that shows up on line 2. So that's just the point, is just to say that this line number is actually really useful in terms of directing you to where you should look in your code to try to solve the problem. Now, we've seen the error types, and there's a little table on the lesson that tells you, what some of those common error types indicate. This usually gives you, in the little text that follows the error message, a bit more information. So list index out of range. That does provide some useful information here. And oftentimes, in the cases of like a syntax error, if I just scroll back up here again, you'll see this little inverted V kind of caret character. It attempts to show you where along the line the error occurred. So in this case, when it doesn't find the second quotation mark for the syntax error above, all it does is put the error indicator at the end of the line. But if you had, for instance, I'm just going to type in or go back to our print statement about my favorite dog here. If I fix this one, put the quotation mark that needs to be there in place, but then I remove the one that is earlier in the print statement and run the same thing, I again still get the syntax error, but now it shows me a different location, because here we've got one quotation mark, we've got a second, and then there's this kind of unexpected exclamation mark here where the code doesn't know what to do. So you can find a little bit more about reading the error messages on the lesson online. I'm going to just do one maybe one quick example using the script that is available on the course lesson. So if I just go here for a second, you can do the same thing. If you go to the Dealing with Errors lesson and scroll down to the second block of script, there's a script in there called windspeed.py. I'm just going to copy that and create a new Python file in Spider and just paste this in here. So what I've done in this case is I have a function here called convert wind speed. I didn't include a doc string because I was being a bad example. That converts wind speeds from kilometers per hour to meters per second. We get some wind speed in here, and then we call that function, and then there's a print statement. It's a pretty simple little program. And I'm just going to run this after I save it as, I guess I'll call it wind_speed.py. It's probably going to complain that that already exists. And I will replace it. So I save the wind speed script, and when I run it, there's trouble once again. In this case, because the wind speed here is given in quotation marks, so it's a character string value. And when I go to do the conversion of that wind speed from wind speed kilometers to the value in meters per second, I divide that character string by a number, and Python can't divide character strings by numbers. What we see here is a little bit longer error message. And probably for most of you at this point, you just panic and stop looking at it because it looks kind of overwhelming to see file, 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 all these different things that just seem to jump out at you. And yeah, in truth, there is a bit of a challenge sometimes when you get these traceback messages, because this is a message that shows you a function that failed within a script you've written and also relied upon some other libraries and things that have been read in. But if you take your time, if you just go kind of patiently, step by step, you can start down at the bottom and you see file, and here's the name of the Python script we ran. On line 11, there's a problem in this function called convert wind speed. And it even shows you which line of that function caused the problem. And that is the return speed times 1000 divided by 3600, where we have this type error. If you look at it just line by line and slowly go through there, you will see there's a lot of information here. We see that we can't use this operation called division with a string and an integer. They don't work together. They're not compatible data types. If you go up from here, just one line or sort of 2 lines up to the next file statement, you see in the same script on line 14, we have a problem because that's where we try to use this function. And then if you continue to go up from there, you'll see there's some more stuff related to the system. And sometimes you'll have some of the different libraries and things or modules that are referenced there. The point is in this case that we have a problem on line 11, but the problem doesn't occur until we run the code on line 14. So sometimes if you're using a function, if you're using a for loop or something like that, you'll see that you get multiple references to the same script that show you different lines. And you should go and then take a look. Okay, here's line 11. And here's line 14. Well, on line 14, I see all I'm using is the function. And then, sure enough, when I go into the function, now I see where the problem is. This stuff is a little bit weird to look at, but it is meant to help guide you. And I think maybe I'll just leave it at that as far as the error messages go for right now. You're welcome to look on the in the lesson for this week for the material on reading through error messages. There's a section down at the bottom with more information where there's some useful links to other descriptions of how to read the error messages and things like that. If you take a little bit of time to learn how to read these error messages, you can save yourself a tremendous amount of time trying to find program bugs. And especially things like just recognizing it tells you what line the problem is on. That can save you a huge amount of effort because there are lots of different programming languages that don't do that. For instance, Fortran is terrible about giving things like a segmentation fault and gives no other information other than your code crashed and you don't know where it crashed or why. Good luck finding those bugs. It takes a lot of practice. Python makes it a bit easier. Also in this lesson, there is a section about assertions. And assertions are a way to sort of check to make sure the values you're giving your code are things that would work. So for instance, with wind speed, it wouldn't make any sense to give a negative wind speed because wind speed is just a magnitude. It's supposed to be from between 0 and infinity. So you could have something like an assertion that would check to see if the user tries to give a negative value, it detects that and then sends an error message saying you can't give this code a negative value. It may well be able to calculate a negative wind speed and do the conversion, but it doesn't make any sense to have a program that gives you values that don't have any basis in reality. So again, we won't use assertions necessarily this week, but they are one way in which you can kind of protect your code and make sure that it does not do things you don't expect it to do. There are lots of good examples of using assertions, and you can see just one in the lesson materials about interpreting errors. There's also some stuff about debugging scripts at the end of the lesson this week, and I think probably we can distill the debugging stuff down to a couple main ideas that are important for you to have in mind. One of them is that if you can, it's best to test your code and to debug your code with some kind of value that you know it should produce. So if we were trying to test some temperature conversion script to see whether it produces a reasonable value for temperatures, even as we did, I think, in the very first week, we wanted to make sure that when you put in 0 degrees Celsius and convert that to Fahrenheit, you get 32 degrees as you would expect. Those kind of things, when you have a known answer, that's a very helpful thing because then you know if you're debugging your code and it runs, but it gives weird numbers, at least you have some target in mind. Another example is something we saw in the lesson already this week, and that is to work with a simplified version of your data set. So maybe take one day of your data, or even something like the example I show in the lesson materials for debugging is you take the first 5 observations. If you want to see whether your code calculates the mean value correctly or calculates the difference between maximum and minimum temperatures correctly, the easiest way to check and see if the code is working is to use some very small subset of the data where you can actually just calculate by hand what the value should be. You don't want to give it 30,000 lines and then have it come up with some number and say, hey, my code ran, so it must be right. Right? It's amazing how often that is not the case. And if you don't have any outside information or any way of checking with just a small amount of data, it's quite likely that you could get some number that looks about right, but could be off significantly, and you just don't know it because you have so much data. Helsinki, I think their group is dealing with millions or even more data points in analyzing social media data, and you have no way of knowing whether you're correct in terms of what the code is supposed to do without being able to sort of check for some small subset of the data that it does what it is expected in that case. And so again, there's an example of that on the materials for the lesson for this week. We won't really have too much trouble. There's a mention about this idea of making sure your code crashes quickly. Normally our scripts don't take a long time to run, so it's more the point that if it takes an hour for your script to run, then it's very hard to debug because you can lose track of kind of what the problem was during that hour. You can get distracted doing other things. But there isn't a point that, it is good to make sure that when your code crashes, it's crashing in the same place reliably. Sometimes it makes sense just to run the code and have it crash, and then run it again and see that it crashes in the same way in the same place. If it doesn't crash in the same way in the same place, you're going to have a very difficult time debugging your problem because it's not happening in the same location. If you're dealing with, for instance, data that's being pulled down online as part of your analysis, and you've noticed that things are not working between different times when you run your code, it could very well be the data source that's the issue. Maybe the website goes down and your code doesn't have any way of handling that, and then it crashes as a result. Those kind of problems can be very difficult to diagnose. For the most part, we won't really have any issues with exceeding memory bounds or things like that, but usually when you get to the point you're starting to make your computer run out of memory, you'll start to see you get crashes at different places in the code in this kind of unusual behavior. And hopefully you don't encounter that. And the last thing in there about debugging is just the idea that, one of the reasons we suggest you use GitHub is because you can take some version of your script that works, make some changes, commit them, and then find out your script doesn't work. And by keeping track of the changes, you at least have the opportunity to go back and figure out, well, what did I do differently between when it worked and now when it doesn't work? Sometimes I even commit things to GitHub when my script isn't working, just because it makes it easy for me to see what's different between the last time I made a change. That's probably the most useful thing about version control, is making small changes and then keeping track of those small changes that you make. So, I'm sorry this is, I know, just kind of an overview of the debugging. You can find a little bit more stuff about this on the lesson page for this week, and also some links for more information about how to debug efficiently.
Yeah, and about the materials about actually seeing changes and differences in GitHub. So is it the first week or the second week? So there in the lesson video there is materials. So during the lesson I actually show you how to do that. So if you're interested, you can go and look from there.
So okay. What I'd like to do at this point is just maybe show you a little bit of this exercise 6, so that you have some idea what's coming and how things are meant to work here. We're continuing, of course, with the idea of doing data analysis using Pandas and, again, processing some kind of weather data. In this case, we're using a slightly different data set. So we've pulled data from this NOAA Global Historical Climatology Network. In fact, you'll do the same thing in the last part of the exercise. But this data, instead of being hourly or even more than hourly data, these are daily values. And they're daily values in this case that go back much further in time. So you're dealing with a data set that's more than 50 years worth of daily data. And so the data files aren't ridiculously big, but they're getting big enough that it's not going to be easy to do much by hand. And in the data sets, it's relatively simple compared to the hourly values. You have only temperature, maximum temperature for that day, minimum temperature for that day, and I think precipitation, and that might be it, other than the geographic location of the station where the data was collected. So your first task is to read in what I call a kind of tricky data file. The tricky thing about it is, well, for one, it's using this fixed width data format, so there's a variable number of spaces between the values. Well, we know how to deal with that already a little bit from the lesson today. But also, the second line of the file is a bunch of dashes that go across. So you have the heading with the names of the variables, then a bunch of dashes, and then the data. Now, I could have taken that out to make it easy for you to deal with, but you can deal with this in Pandas You just have to have some way of eliminating that second line and then continuing to read the data after that. Because if you read the second line, Pandas looks at it and says, oh, this is character string, and makes all of the rest of the data character strings. So you're going to have to find a solution for that. Of course, we've already given some hints about how to deal with that for the hints for this exercise, but if you want to try and find one on your own, this is a good excuse to go on to Google and to browse through things like various websites where people post their problems in Python and try to find a solution. Really, the main goal for the first problem is just to read in the data file, and then you just have to calculate a few things about that data that you read in. How many not a number values are there? So how many real observations do we have for the average temperature? Things that are just, basic information about the data file. Yeah, it's been fixed. If you checked out the version of this exercise earlier using the GitHub Classroom link, there was this initially said what was the T average temperature for the summer of '69. There is no data for the T average for the summer of '69 in the data file, so instead you can use T max. We'll maybe put that in the hints or somewhere else, maybe on Slack for the exercise. Problem 2 is to take this daily data and convert it then to monthly average temperatures. So just to take each of the days within a given month, average them together, and then essentially do this data aggregation that we did previously when we had more than hourly data and took that down to being hourly data. And you're going to do that. I've kind of outlined one way to do it here. There are more than one solution or more than one way you can do this. But once you calculate the monthly temperatures, they're in Fahrenheit, and so you should again convert those to Celsius and save them in a new Pandas data frame. And there's an optional problem there if you want to try and use this date time index in Pandas. It's super cool, but we didn't introduce how to do it, so I was all excited about this because I was learning Pandas like in the last week, and I'm like, oh, this is so awesome, but it is also not necessarily that obvious how to do it. So after that, we get into something that's kind of fun, I think, and that is to calculate temperature anomalies. And so what you're going to do is you're going to calculate the mean temperature for instance, the month of January from the start of the data, which is in 1952, until 1980. This is going to be kind of a reference period of time where we have the average temperature for January for all of those years. Do the same thing for February, March, April, etc. So you'll have 12 different average values, one for each month between 1952 and 1980. Then you're going to go and calculate the temperature anomaly for every observation that we have from the monthly average temperatures. So you'll look at the January of 1952 and say, how does that compare to the average for all of the January months in between 1952 and 1980? If you remember back to the first week when we had this little animation of these global temperature anomalies, this is basically the same kind of idea that we want to calculate in each month how much does the temperature deviate from the average value in this reference time period. And the thought is that if we can do this week and it works out okay, that we have something fun then to be able to plot for the exercise next week, where we can kind of, we won't make a nice little circle necessarily with things that go like this on the edge of the circle, but we may be able to plot the trends in terms of the temperature anomalies through time and perhaps see how temperatures have been changing, presumably warming, but last year we sort of found a place where it was cooling down instead. But we'll do that by calculating the difference between a given month's average temperature and the reference time. So that's the temperature anomaly. And it's spelled out a little bit more clearly how to calculate that in the description of problem number 3. Then finally, in problem 4, it looks like you're asked to download your own data for the Rovaniemi lentoasema, so the Rovaniemi airport station, and
so the idea is to kind of take the stuff that you did in problem 3, but to do it in a different place, so in Rovaniemi, and basically then see if there has been differences between Rovaniemi and Helsinki dataset. So that's the kind of basic idea.
Yeah. So one of the common ideas in terms of this global climate change is that high latitude climates are more sensitive to the changing climate than low latitude climates, and maybe we'll see some difference between, for instance, Rovaniemi and Helsinki. So that's what you're asked to do. I think you guys have the skills to do most of it, and we will provide some hints on the website to deal with some things that we anticipate will be problematic.
Yeah, and we will still update the hints page, so there is already some stuff, but some missing, so it will be updated.
Yeah, so keep an eye on that, and if you have questions, please post them in Slack or come Thursday or Friday to the work sessions.